Greetings. About a year ago, I did a bunch of videos on the Motorola MC6800 microprocessor. We started with some assembly language basics, and we then went on to a simulator, a homebrew simulator I had written to execute 6800 code and basically use one of these trainers. I simulated this trainer so you could run code on it and verify things. But the bottom line was that wasn't a whole lot of fun. So I finally found an ET3400, which is the original trainer, on eBay. I'd been looking for a while, but these things have gone up in price just like everything else. This one was significantly cheaper than all the others offered. And it showed a picture, a blurry picture of it that looked like this. Looks like it's powering up, but it's not. It's supposed to say CPU up, meaning that it's running, and it's not running. And the picture it was blurry. I couldn't tell what it was showing on the displays, but it looked something like this. And the ad copy said ET3400A trainer, please read, or must read description, or something like that. The only problem with it was the description field in the ad was empty. It was blank, so somebody forgot to put it in. But I looked at it, it was reasonably priced, and what this indicated to me was the CPU wasn't running on it. So how hard can that be to fix? We'll find out. But first, a brief tour of this wonderful device. Again, this is the Heathkit ET3400A. So the ET3400 with no A came out in 1976, and it had an MC6800 processor, 6-7 segment displays, has a keypad, and assorted logic, and it's kind of an interesting setup with the PCB on top, with all the legends on it of what these chips are doing, and access to most of the signals coming off of the processor. For instance, the entire address bus is here, control signals are here and here, the data bus is over here. So you can wire things up. They had educational systems, documentation for this, where you went through a bunch of experiments, and it was actually quite cool. Now, notice that I said the original was without the A suffix, and that one came in a blue case. And arguably the blue case looked a little bit, looked a little bit better than this case. The beige is kind of ho-hum, but this is the A, and this is the second version of the A, which actually uses an MC6802 processor. And this one looks like it was a little bit better built, had some upgrades. The circuitry is a bit different, but the biggest difference for me is that the keypad on the original was really flimsy. And they just weren't, the mechanism wasn't very well built. And on this one, it's got a really nice, good keys, sturdy keys, and also where the legends won't rub off. And this thing, it looks new and unused. And that's probably because it didn't work right. So the first thing we need to do on something like this is check voltages. We have voltages coming out over here, 5 volts, plus 12, and minus 12. So let's see what kind of voltages we're getting. Well, the 5 volt looks good. The plus 12 looks good. Minus 12 looks good. So we got good voltages coming out of it. Nothing's getting hot or smoking. So let's start checking this thing out. I poked around a little bit here with a period correct logic analyzer, logic probe, to see what was going on, and it looked like clocks were getting to the processor. Well, the clock is getting to the processor because unlike the 6800, it uses a single phase clock, divides it down, and creates all of the reference clocks on chip. And that's the main difference in the pinout. That's why it's hardware incompatible. Well, you can't put a 6800 in here because it won't run. But the clock was coming in, all of the external inputs were correct. But what I noticed was that the chip acted like it wasn't doing anything. It was getting a clock, but all of the address lines and all of the data lines were floating, which usually indicates that somebody is in a bus request state or a bus available state, which means if you wanted to do DMA or something, you could request the processor to make the bus available, and then it would tri-state the address lines and the data lines and some of the control lines, and you could do DMA or whatever, have access to the bus without the processor interfering. And that's kind of the way it was acting, except the bus available signal was not active, and it looked like it wasn't doing anything. So the first thing to do for me is, on older things like this, check the ROM. Pull the ROM, I checked it in my ROM burner against a known good ROM image that I got off the internet, and it checked out. But while I was at it, I burned the image I got off the internet onto a new 2716, and nothing changed. So now we had to start checking individual chips. As you can see, everything is socketed on here. There's also some chips underneath here that I remember are also socketed, but I started with taking everything on the board and checking it. And what I used for it was, I have yet another toy. It's this programmer here. Can you see that? Yeah, kind of. It is the XG GCU model TL866I Plus. They sell for about $60 or so on eBay, a little cheaper if you get them from China. I mean, I call it a toy because it is a toy. It doesn't, when it checks TTL chips, it doesn't, I don't think it loads them properly or makes an attempt to. It's an artificial environment, but as it turns out, it's actually a really good tool that gives you, that at least gives you a go, no-go on the chips, because I have a pile of bad chips that I used to test this, and it identified all the bad chips and actually told me that some of the chips in my bad pile were good. But I checked all of the chips that I could. Some of them I couldn't. It's got two 2114 RAMs on here that the programmer cannot test, and of course it's got the CPU. So I think the next step here is to open it up and see if there's any other, well, I think there's other chips in here, and see if we can test those too. So the top has been removed. You do have some more chips in here. I tested what I could here. Basically, these 6 are 7-segment decoders, latches, that each one for each of the displays, so they don't scan them. There's no flicker here. There's not supposed to be any flicker. Bunch of decoding logic over here that tested good. The only other thing is an op amp that is used. I mean, one of the features here is that it generates a 1 hertz pulse. And that has nothing to do with the processor. That is directly derived from the line frequency. And what we can do is basically it's labeled as 1 hertz. And we put it into one of our LED monitors here. And when we turn it on, we will see that it's generating a 1 hertz pulse. So that basically told me that everything up here tested out good, but things were still going weird. One thing I observed by chance was when I removed the EEPROM, I kind of tested things. You know, the processor can't do anything sensible, but it seemed to be running because all of the address lines and the data lines came alive when I pulled this out. I mean, it was nonsensical. I think it was just iterating throughout the entire memory space and doing whatever, but it showed me that the address lines and data lines were in fact active, working, and all the address lines are buffered, the data lines are buffered, and the control signals are buffered. So that also told me that the buffers, which tested okay on the chip tester, did seem to do their job. So this should give us tremendous clues. You pull the EEPROM, the processor starts running. Even though he's in the dark, he's still running. But the minute you put this in, it stops. So some of the data, some of the instructions it's pulling off of here are making it do something very, very odd. So at this point, I think our problem is down to something bad on the board. And you may ask, why didn't I put in a new processor? I did try. I had a regular 6802. I put that in, and it did the exact same thing. Comes up like this. When the EEPROM is in there, address and data lines are floating, and nothing else is happening. So we got to dig a little bit deeper. At this point, I was kind of stuck, and for lack of better idea, I started testing continuity. I started testing connections, which can be quite a big job, but I didn't know what else to do, really. So that's what I did, and everything seemed to work out, but when I hit this chip, there seemed to be a bunch of intermittent connections between the socket and the chip. And that was interesting, but what that was due to, I don't know if you can see that at all, but there's liquid damage on some of the contacts in the 20-pin contact, in the 20-pin socket. It's almost like somebody was salivating over this or drooling over this while being pissed off that it didn't work. But yeah, it hit the socket, and it's, again, it doesn't show up nicely, but it's got a lot of white corrosion on it. And I was getting intermittent connections. Well, so a new socket went in, chip went back in, and we get nothing. Time to get discouraged? Not at all. Continue checking continuity and connections and all of that. And I was checking the connection between these guys here, which give you access to the data, to the address bus. See, they're labeled above. Make sure that these were connected properly because the address bus is buffered. Basically checked whether all of these were properly going to their respective buffers. And then the universe was kind to me, because as I continued doing this and, probing from one to the next, I found a short. It turned out that address line 3 and address line 2 and address line 1 over here were dead shorted to each other. So I went back again, I pulled every chip, I checked again, and A1 and A2 were still shorted. So something going bad on the board. Now, with the solder mask here, you can't really see what's going on, but I looked, there really isn't any damage on top of the board. So it's got to be underneath somewhere. So that's what we'll do next. Here's the underneath of the board. Obviously traces are a lot easier to follow here because there's, the whole thing isn't covered by a white solder mask. Here these shiny pins are the socket I replaced. And I had to guess, if I had to find the places on the board where buffered address line 1 and 2 were physically close to each other. So I started over here, which is the other side of the connecting points. These are the white 1x4 blocks that give you access to all of the address lines. And here's A1 and here's A2. And I found something. Here is address 1, and here's address bit 2. And when I looked at this closely, it almost looked like the pads on this pin and on this pin were connected to each other. So I'm trying to rub it, see if there's something in there, corrosion in there, using a knife. But the more I looked at it, it just looked like the pad for some reason was extending from here to here, dead shorting it. Now that's, you might say that's impossible, but it wasn't impossible. So what I did, before cutting it, just to satisfy my curiosity, and let's clean this up a little bit first, because there's still some left over from when I cleaned it up. So instead of going ahead and just wildly cutting what looked like a pad, let's try to get an even better shot of this. Yes, between this pin and this pin. So I took some desoldering braid and heated up the whole area and removed all of the solder here. And lo and behold, the thing that I thought was a bridge on the pads was a solder splash. I mean, I don't call it a bridge. Well, it is a bridge technically, but a bridge usually you see a big blob between two pins. But this was just flat on the ground and looked like these two were connected. But it got, the solder wick sucked it up. So somebody dropped a very tiny bit of solder on here that flattened itself to the PCB, yet connected these two pins. Very interesting, but that kind of implies to me that it looked like it was a manufacturing error. So this must have gone through an interesting industry where people bought it, because this is pre-assembled. This was not assembled. It doesn't look like it was assembled by somebody at home, but rather factory assembled. But I may be wrong. Maybe they were really good at soldering, because pretty much they looked. I know these soldering, these joints don't look like they were wave soldered, but I've seen assembled ones before, and the Heathkit stuff just wasn't fantastically soldered. So I don't know whether this was factory done or home done. It doesn't have a W in its model number, which usually indicates that the W models were factory assembled. So maybe somebody did assemble this at home and did a pretty clean job. except they messed up big time over here. So the minute I removed that solder bridge, the short disappeared. And now let's see how it performs. So I even put back the original EEPROM, and let's see if we fixed it. 3, 2, 1, go. Boom! That was a solder bridge. So now, does the keyboard respond? Let's see. Contents of accumulator A, B, program counter, stack pointer, condition codes, index register. Yep, everything seems to be working. We can examine memory. The ROM starts at FC00. And I stared at the ROM listing many times, and that looks correct. So we can go forward to examine memory, backward. And usually one of the things to look at is the reset vector area, which is at the very top of the EEPROM, because that's the first thing the processor fetches. So if we do an examine and we go to FFF8, let's see, that's not it. I think the next 2 bytes are the starting. No, the very last 2 bytes are the vector of where the processor resets to. So we need to go to FFFE, and it tells us that the starting vector is FC00. And as we can see, the ROM occupies, let's see if that is visible from here. Yeah, the ROM occupies memory address FC00 through FFFF 1K. That's where everything is. And that's why I guess it works. So now one thing we can do, we can press the do key. That's basically a go to or run from. And then tell it to go to FFFE. No, that's the vector. We want to go to FFC. No. Try it once more. FC00. That's, boom. That's where it starts, and that's where everything is. So let's put this guy back together again and do a final test by entering a short example program out of the manual. The only real blemish on this thing is it looks great, new and almost unused, but somebody went to great pains to remove a label or writing or something from here to obfuscate where this came from or who the owner was. I don't know. Things people will do. However, if you look at this label, I was right. If you look at the model number, it's ETW-3400A. The W means that this was assembled at the factory. So it wasn't like some poor soul put this thing together and could never get it to work, but they messed up at the factory. And I don't know how this thing got through their quality control. So as a final step, we should probably enter some code that does something. And there's a short example program in the manual that looks like this. And turn on and off each segment in sequence beginning at H display, blah, blah, blah. And the way we do this is, the only way we can do it is to enter the machine language. So we are entering bytes. And here we go. So the way we enter code, well, first we reset it, then we go to auto, and we enter 0000, which is where our code's going to go to. And yeah, so let's see. Sit back and enjoy. BD, FC, BC, that's a call to the monitor subroutine. Set up first display address. 8601, load accumulator A with 1, branch to label out 2007, and then, yeah, I'm not going to read the machine code, it's just D6, F1, and I typed really quickly. We're at the last line, which is 20 EA. So now the program's entered. We could go and check it, but let's just run it. And the way this works is after, to get out of all these commands, you hit reset. It's non-destructive to user memory, but I guess that saved them a lot of code to not have to implement an escape key. So what we do is we say do 1, 2, 3, 4. And you can observe it going through all of the displays. And though it's hard to see, it's also lighting up the decimal points. So there you have it. It seems to be in full working condition. There's lots more things that can be done with this. You could buy an expansion chassis for this that kind of fit underneath here, connected to a pin header, and gave you more memory, a serial port, and a bunch of ROMs, including Tiny Basic. So you could hook up to this with a terminal program and write Tiny Basic programs for it. But more on that in a future episode. Thanks for watching. Give me a like and a comment, and we'll see you soon.